In finding the normal modes of oscillations of coupled system, we have till now discussed a very important example of two coupled simple pendulums. First of all, you have seen the problem of the two identical coupled pendulums, and after that we have seen the general result. Now today we are going to see a new example of this coupled system. Actually, in this example, you will see there are two masses coupled together by the massless and linear spring. And when the two masses are actually displaced from their equilibrium position, they will oscillate simple harmonically, and we have to find the normal modes of oscillation of such a coupled system. So this is the problem of finding the normal modes of oscillation of two coupled masses. Here again, for simplicity, I am first of all considering that the two masses are of equal value. As you can see in this figure A, I have shown two blocks of A and B whose masses are m, each of mass m. Okay, and these two masses are connected by three springs, as you can see, and the spring constant or the force constant of each of the spring is also same, and that is equal to k. Okay, so this is the simplest situation. In fact, in this example, you will see there are two possible modes of oscillation. First of all, we will see the normal modes of oscillation, and after that the transverse oscillation. We will actually discuss to find the normal modes of longitudinal oscillation and the transverse oscillation separately. Okay, so in this first part of this lecture, you will see just the discussion of finding the normal modes of longitudinal oscillations of this two coupled masses system. And for this, you can see, as I have shown in this figure 1a, that the two masses M, A and B are connected by three springs, and the masses are lying on a frictionless horizontal surface. Actually, in figure A, we have considered that the three springs are relaxed. They are in their natural length. And in other words, you can say the springs are neither extended nor compressed. Okay, so you simply say that the system is in equilibrium. Now let us consider from this equilibrium state of the system, the two masses are displaced horizontally on the surface, so that the longitudinal oscillation will take place. As you can see, that mass A has been displaced by psi A from its equilibrium position at any moment t, and at the same time mass B has been displaced by psi B. In general, psi A and psi B are not equal. So when this system is disturbed, or this system is perturbed or displaced from its equilibrium position and released, what will happen? Actually, under the restoring force exerted by the springs, the two masses will oscillate about their equilibrium position, and for a small displacement their motion will be simple harmonic. Okay, actually our aim is to find the frequencies of oscillation of this system. Okay, and for this, for simplicity or for calculation here, I am just considering the case that displacement psi B of block B is greater than psi A. So when psi b is greater than psi a, actually in that condition, this first spring will be elongated or extended. Okay, this second spring which connects the two masses, or you can say this is third spring, this is second spring, this will also get extended, but the second spring will be compressed. Okay, now taking the forces acting on the two blocks, you can write the equation of motion of this system. As you can see, I have actually mentioned all these things here for your convenience, which I have just explained. That has been written here. You can note down these things in your notebook. For convenience, I am just giving a reading again. This is just a repetition what I have told you. Let us consider a system consisting of two masses and three springs connected as shown in figure 1. In the simplest case, we consider each mass equal to m and each spring of a spring constant or force constant k. This system is capable of longitudinal and transverse oscillations. These two types of oscillation will take place in this case. And as I have told you, in this present lecture, we are going to see the discussion of normal modes of longitudinal oscillation only. In the second lecture, we will see the normal modes of oscillation of transverse vibration or transverse oscillation. Okay. And as I have told you that in figure 1a, the system is in equilibrium state, and from that equilibrium state, the system is slightly perturbed or slightly displaced or slightly disturbed. And at any moment t, this psi a represents the displacement of block A and psi b represents the displacement of B. Okay, and if the system will be released, it will oscillate longitudinally. And for our calculation here, we are just going to consider psi b is greater than psi a. So when you will take psi b greater than psi a, then the forces acting on the two blocks will be what I have shown in this free body diagram. You can see this point mass actually represents block A of mass m. You know, the forces acting in these on this block will be what? One of the force will be force of gravity mg, which acts in downward direction, as you can see. The another force is normal force or normal reaction due to the horizontal surface on which this block is lying. Now, this spring 1 is elongated, so it will pull the mass A towards itself. So, as psi A is its elongation, so k times psi A will be the spring force developed in the first spring, which will act on this block A, and it is acting in leftward direction. Okay, but as you know that this spring number 2 has been compressed because psi b is greater than psi a, and this displacement of A is psi A and that of B is psi B, and psi B is greater than psi A. So the net compression of this second spring will be actually equal to psi B minus psi A, and so the force exerted by that spring on it will be what? That will be k times psi B minus psi A, and this force actually acts in the rightward direction. Okay, so and this mass has acceleration in this right direction. This is psi A double dot. So take as The block has no acceleration in vertical direction, so mg is just balanced by n, and net force acting on this block on this horizontal line in the direction of its acceleration psi a double dot, which means d2 psi by dt, will be what? That will be k times psi b minus psi a minus k psi a. So you can see I have written here the equation of motion for A like this. This is mass times acceleration of A, which is psi A double dot. That will be equal to K times psi B minus psi A minus K psi A. Okay? And so you can write psi A double dot equal to minus K over M times psi A and plus K over M times psi B minus psi A. This is the equation of motion of system A, or you can say block A. Now let us see what will be the forces acting on this block B. Actually on this block B, one of the force will be due to this spring number 3, as this spring has been elongated by psi b, so it will exert a force k into psi b on the block B, okay, in leftward direction. And a spring 2 is actually now compressed. This is compressed by psi b minus psi a, okay, and so this will exert a force on this block B, which will be k times psi b minus psi a, and that will be also in the direction of this k psi b because it has been compressed, okay. So this block B will experience two spring forces, k psi b times k psi b minus psi a, both in leftward direction, okay. So you can see the free body diagram of B. This force k into psi b plus k into psi b minus psi a, both are acting in leftward direction on it. And again this mg is balanced by n, so net force acting on this block B in leftward direction is k into psi b plus k into psi b minus psi a. But its acceleration is psi b double dot, and it is directed in rightward direction. So the forces acting on it are just in opposite direction of its acceleration. So according to Newton's second law of motion, you can write the equation of motion like this. This is m times psi b double dot equal to minus k psi b minus k psi b minus a. Why minus? Because these forces oppose the acceleration, okay. And so you can write psi b double dot equal to minus k over m into psi b minus k over m into psi b minus psi a. So these are the two equations of motion of our system. Actually the frequencies of the normal modes can be determined by guessing the normal mode configuration from symmetric consideration, or by using the method of searching for normal mode coordinates, which you have learnt in earlier lectures. Actually here we will follow the symmetry concept. As you know, in case of a coupled system, the frequency and the phase constant of oscillation of all moving parts for a particular mode of oscillation are same. This is a very important property of normal modes, okay. So for convenience here, let us consider that the existence of a normal mode at a frequency omega and phase constant phi. You know, if here in this example there are two moving parts of the system, one is A and another is B, and both will oscillate with same frequency omega and phase constant phi in a particular mode. Okay. So in a particular mode, as they will oscillate simple harmonically, so the displacement psi A and psi B can be written in terms of the cosine function or sine function or exponential function, as you have learnt in your course on simple harmonic motion. Okay, so you can write psi A equal to A times cos omega t plus phi. Here A is the amplitude of oscillation. Okay, and similarly psi B is equal to B times cos omega t plus phi. Here, since A and B both are the moving parts of the system, and so in a particular mode, both will have actually same frequency omega and same phase constant phi. Okay, but the amplitudes A and B may be equal or may be different. It depends on the mode of vibration. Okay. Now, from these two equations, we will obtain the acceleration of A and B. And for getting the value of acceleration, what you will do? You have to simply differentiate these equations 2 times with respect to time. Okay. So let us try to find the acceleration. So differentiating this first equation with respect to t, we will have d psi A by dt, which is just equivalent to psi A dot. In dot symbol we write it psi A dot, and that will be equal to what? That will be minus omega A sine omega t plus phi. And so that when you will find d2 psi A by dt square, which is just equivalent to psi A double dot, that will be equal to what? That will be minus omega square A times cos omega t plus phi. But you know, this A cos omega t plus phi, this is equal to psi A. So instead of that, I have written here psi A. So psi A double dot, this is equal to minus omega square psi A. Okay, this is just equation of motion of simple harmonic motion. Okay, because here you can see that this psi A double dot, which is acceleration of A, this is proportional to minus psi A, which represents that motion of A is simple harmonic. Okay. Actually, in the similar manner, when you will find by differentiating this equation psi B equal to B cos omega t plus phi 2 times with respect to t, you will get psi B double dot equal to minus omega square psi B. And so you can say that B will also oscillate simple harmonically, okay, with frequency omega. Now we will substitute the value of psi A double dot in equation 1. Okay, in equation 1. So let us put, since you have seen that this psi A double dot is what? This is minus omega square psi A. So instead of this psi A double dot in LHS of equation 1, we will write minus omega square psi A. So you can see I have written here that this is minus omega square psi A, and RHS remains same. This is minus k over m times psi A plus k over m psi B minus psi A. Okay, and you can see this is minus k over m psi A plus k over m psi B minus k over m psi A. So this minus k over m psi A and minus k over m psi A will be added, and when it will bring into the LHS, that will be 2k by m psi A. So taking psi A as a common factor, you can write 2k over m minus omega square times psi A is equal to k over m psi B. And so psi B by psi A, this will be 2k over m minus omega square over k by m. You know, this ratio psi B by psi A is called shape or configuration of a mode. Okay, shape or configuration. Okay. Now, again, substituting psi B double dot equal to minus omega square psi B in this equation number 2, you can obtain the value of psi b by psi a. So let us replace this psi b double dot by minus omega square psi b, and substituting that, when you will do the algebra in similar manner, you will find that psi b by psi a is equal to this much. I have not done this algebra here, this is just like above, and you can do it. So psi b by psi a, in this condition you will get k over m divided by 2k by m minus omega square. Okay. So you can see we have obtained the value of psi b by psi a in equation 4 and also in equation 5. Okay. Now if neither psi a nor psi b is 0, then equation 4 and 5 will hold simultaneously only when the RHS of equation 4 and 5 are equal. So now let us equate the RHS of these two equations. So equating these the RHS of equations, you will get this is 2k over m minus omega square over k by m is equal to k over m over 2k minus m minus omega square. Okay. Now let us simplify this equation. Making the cross multiplication, you can see we will have 2k over m minus omega square whole square is equal to k square m square. And so 2k over m minus omega square will be what? That will be plus minus k by m. Okay. And so you can write omega square equal to 2k by m minus plus k by m. So you can see, taking the minus and plus sign separately, we will have two values of omega square, which actually refers that there will be two mode of vibration. We will call them mode number 1 and mode number 2. So from this result, it is evident that there will be two possible values of omega square. And what will be those values? You can see, if you write the first value of omega square as omega 1 square, then that omega 1 square can be obtained by taking minus sign here. So omega 1 square is equal to 2k over m minus k by m, and that will be simply equal to k by m. And so you can say that omega 1 is equal to a square root of k by m. Okay. Now the another value of omega square you can find by taking plus sign here, and so you can say this omega 2 square is equal to 2k over m plus k by m, and so this is 3k by m. Okay. So you can see that this omega 2 square is not equal to omega 1 square, but it is 3 times of omega 1 square. And so you can say that omega 2 is equal to a square root of 3k by m. So these omega 1 and omega 2 are the two normal mode frequencies. Okay. If you call that omega 1 is the frequency of first mode and omega 2 is the frequency of second mode, you will see that this first mode will be called in phase mode, because in this condition both the masses will oscillate in same phase. So let us see the case of in phase mode, that is first mode. Actually, if your aim is to find the shape or configuration of mode 1 or in phase mode, you will have to put omega 1 at the place of this omega either in equation 5 or in equation 6. Sorry, either in equation 4 or in equation 5. Okay. So let us substitute omega 1 at the place of omega in equation 4. Then you will get actually this psi b by psi a, that is shape or configuration in mode 1. So in this case, psi b over psi a in case of mode 1, what will be this? you can see from these two equations that psi A is equal to this much and psi B is this much. So from here you can see that this psi B by psi A is equal to what? This is simply B by A, that is ratio of the amplitudes. And so you can write that psi B by psi A in mode 1 is equal to B over A in mode 1. And we write it as B1 by A1. Here the subscript 1 refers mode 1. Okay. And for getting its value, as I have told you earlier, that we will put omega 1 square, which is equal to k by m, at the place of omega square in equation 4. So you can see this will be equal to 2k over m. Here there was minus omega square. Now omega square will be replaced by k by m in case of first mode. So this is 2k by m minus k by m over k by m. So this is simply what? This is actually k by m over k by m. And so these two will cancel out and your result is plus 1. Actually, this plus 1 shows that both the masses will oscillate in same phase. And therefore, you can also say that in this case, first mode, the amplitude of oscillation of both blocks or both systems are equal. Okay. Now we will see the frequency of the shape or the configuration of the second mode of vibration, which will be called actually out of phase mode, because in this case you will see the two masses will oscillate in anti-phase, that is, there will be a phase difference of 180 degree between them. And again, if your aim is to find the shape or configuration of this second mode, which is taking place with frequency omega 2, you can obtain this simply by setting omega 2 square at the place of this omega square, either in equation 4 or in equation 5. Okay. This will be okay. Page has been turned, but this is not a major problem, as you can see. Sorry. So let us see. When you will substitute omega 2 square at the place of omega square in this equation 4 or 5, you will get the value of psi B by psi A in mode 2, which is called the shape or the configuration of the mode. Okay. So let us see what will be this. This psi B by psi A in mode 2, this will be equal to B by A in mode 2, and we write it for convenience B2 by A2. And what will be that? I am again putting the value of omega square, which is omega 2 square, in equation 4. So this will be 2k over m minus omega square. But in this condition, omega square is equal to omega 2 square, and that is equal to 3k by m. So this will be 3k by m and divided by. So you can see this is simply minus k by m over k by m, and so both will cancel out and this will be minus 1. So the shape or configuration of mode 2 is equal to minus 1, and this minus 1 actually implies that in this case B2 is equal to minus A2. That is, the amplitude of both the oscillators are equal but opposite in sign, and that's why we say that they are out of phase. There is a phase difference of 180 degree between them. So this is all about the longitudinal oscillation of this two coupled masses. But as I have told you that in next lecture we will see the normal modes of transverse oscillation of these two coupled masses. Okay. I think this concept was very simple, and definitely if you have watched this video seriously, everything have been clear to you. Okay, thank you very much.